We saw symmetric matrix vector multiplication as an example in the beginning of this week. What we're now going to do is look at a very closely related operation, symmetric matrix multiply. Okay, and what is that? Well, what if you're trying to do C is equal to A times B plus C, except A is a symmetric matrix? All right? So let's start by coming up with the partition matrix expression. Okay? And what did we learn from coming up with algorithms for matrix multiplication? Well, we learned that we should pick one of these operands, we should partition it and then see what happens to the other ones. And notice that it might be beneficial to start with the operand that is sort of most special. And which operand is most special? Well, operand A, which is the symmetric matrix, is most special. And we noticed before that a symmetric matrix we want to partition into quadrants because we want to somehow be able to play with that symmetry that exists. All right. So what does that mean? We have this as the postcondition. Well, we have this as the postcondition. And now what? Well, let's partition matrix A. And how did we partition this when it was symmetric? Into a top left, a bottom left, a top right, and a bottom right, like that. And then what we did was we recognized that if we chose these to be square, and we only stored the lower triangular part, then this right here was actually just the bottom left part of A transposed. Okay? So we take that and we plug it into the postcondition. We've done that before. And then we say, well, how should everything else be partitioned? Well, notice that we learned that if you multiply with a partitioned matrix, you should do this times that plus this times that, and this times that plus this times that. So that indicates to me that B should be partitioned into a top part and a bottom part at the very least. But you could of course say, well, since we partitioned A into quadrants, why don't we also partition B into quadrants? Well, there's nothing special about B. It doesn't have any special structure. At least we haven't said so. And therefore we want to partition it as little as possible. We know we must partition it this way, but we don't need to partition it any more than that. So let's leave it alone. Okay? Okay, now notice that when you do this times that plus this times that, you end up with a top part. And this times that and then plus this times that gives you a bottom part. So that tells us that C must be partitioned into a top part and a bottom part. All right? And that of course means then that C hat should be partitioned into a top part and a bottom part as well. You got it? So what did we always do? You take the postcondition, you partition one of the operands, you plug it into the postcondition, you then figure out how everything else needs to be partitioned. It gets us to this state, and then what? Well, then we needed to be able to figure out what operations need to be done with the exposed pieces, because that then allowed us to systematically come up with a partial result towards the final result. All right? So what do? We say, okay, well, let's actually take this and let's actually multiply it out and see what comes out so that we know what operations must be done with the different pieces. Okay, so let's multiply it out. We get this times that plus this times that. Which must be added to that. We get this times that plus this times that, which must be added to that. Okay, so now we have this, which by the way looks exactly like what we had when we did symmetric matrix vector multiplication, except these were lowercase x's and those were lowercase y's. Right? It should look very familiar. And since it looks so familiar, you should be able to just go ahead and find all of those loop invariants. Right? And then you should be able to go ahead and find all of the algorithms. And then you should be able to go ahead and find blocked algorithms where you simply say, well, let's actually go ahead and partition off not just one row and one column at a time, but multiple rows and columns at a time. All right? And why don't you go ahead and do that? And by now you should be really fluent, so this should just happen really quickly. Okay? And then I'll see you in the next video.